Okay, when we were talking about work energy theorem on Tuesday, we talked about how it means that work is a change in energy. Okay, that's essentially what work energy theorem says. Now, what that can end up meaning is that since work can be calculated by multiplying force times distance, or by calculating the change in energy, that would be final energy minus initial energy, what often happens is these two things get set equal to each other mathematically. Okay, so in the questions we had in the quiz, we didn't have to do the force times distance part because they told us what work was. Okay, so they actually gave us the number, which eliminated having to have force times distance on one side. That's not usually the way they're going to go. Usually you're going to have force times distance on one side, and you're going to have the change in energy, either potential or kinetic, on the other. Okay? Oftentimes, the initial energy will be zero, which makes them quite easy because then you don't have any subtraction on the other side. Okay? But sometimes it won't be, and that just means you got to do a subtraction operation. Maybe you got to add something somewhere. Okay? So, what I would like you guys to do is to copy down these steps. These are the steps to solving any work energy theorem problem. Okay? I'm going to take off the parts I drew on here. Okay? If you write those down, we're going to kind of just reinforce those steps over the next few days so that we get the hang of how to do these work energy theorem problems. Because on Tuesday I told you they're very patterned. Okay? Every single one we did followed the same pattern. So whenever we encounter a work energy theorem problem, these are the steps we want to follow. The first thing is just to write out the givens. And while you're writing out the givens, you want to visualize the question. What's happening here? Okay? Be able to see it. From that, you can determine, okay, that obviously work equals a change in energy, but then for step 3, you would know, is it potential that's changing or kinetic is changing? And the way you tell that is pretty easy. If you're given a change in height, it's potential. If you're given a change in speed, it's kinetic. It's what those two energies go with. Height always goes with potential. Speed deals with motion. Okay? So you're always going to be dealing with one or the other. And in Physics 20, we have questions that involve both at the same time. Right? It doesn't actually make them any harder. You just have both changing. Okay? But in Science 10, you only have to deal with one type. Okay? So you just determine which one it is, and then you set up work energy theorem. And what I mean by that is you say, all right, the work, force times distance, is equal to the change in energy. That might be EK final minus EK initial, or it could be EP final minus EP initial. It just depends on what the question gives you, right? And then from there, you set this up. Okay? You either have force times distance equals the change in potential, or you have force times distance equals the change in kinetic. And at that point, sometimes you can cancel one of them off. Okay, if it starts from rest, for example, in a kinetic question, then you can cancel off the initial. Okay? If it starts from the ground in a potential question, you can cancel off the initial because it doesn't have any initial energy on the ground. Everyone follow me there? There are little things that you get from the context or the story in the question. Okay? All right, then you just manipulate for whatever it is you're looking for. So you do your algebra so that what you're looking for is isolated, plug in your numbers and solve. Okay, so there's really only 5 steps, and some of them are all in your head. Okay, like determining what kind of energy is changing, visualizing. That stuff's not stuff that ends up on paper. Okay, it's stuff that you have to figure out. All right. Give this one a try here. Okay, you got a person who uses an unknown force to lift a 50 kilogram mass to a height of 1 and, actually, you know what, no, hang on, don't do that one. That one's got a weird thing in it. That one. Okay, so heavy box, 35 kilograms, is pushed up a hill by a force of 150 newtons over a distance of 25 meters. How much higher is the box at the top of the hill? We're going to assume that we started at the bottom. Okay? Write that one down. This is, I don't know how many times I've given a question like this on a test. Okay, but that's very, very typical. All right, I'm not gonna do the whole thing, but I can see a couple of people are stuck, and I just wanna give you what might give you a little push to get going, okay? So if we're pushing a box up a hill, sometimes it's handy to just draw a picture of the situation, okay? I do it all the time, even though I can't draw, okay? So we push something up a hill. We're gonna start here at the bottom of the hill. What's my height here? 0. Okay, so this can be kind of part of my givens. My initial height is 0 meters, okay? They want to know, how high am I here? That would be my final height. Agreed? Okay, so I'm looking for that. Right? In order to make something go up a hill, I have to push it. And I'm going to push it using 150 newtons worth of force. And I'm going to do that along the length of the ramp, which is 25 meters. Right? That's what they said, 25. Yeah. Okay, so 25 meters is a distance. Okay. Is work being done? Yeah, it's work to push something up a hill. Okay, for sure. Work is being done. Am I changing the speed of the object at all? It doesn't mention it, so we have to assume that we're not. Okay, but we are making the object go up. Okay, when we get to the top, we will be vertically higher than we were before. So what kind of energy am I changing about the box? It's potential energy. Okay, so that means that this question is a change in potential energy question. Okay, and now you've got the formulas for work. And if you go back to those steps you just copied down, you'll actually see the expanded version of that formula in, I think, step 4. Okay, if you go back and look at that, I'll give you a little bit more time to see if that gets you kind of a little push. All right, so we've established that when you move something up a ramp, as long as you don't accelerate it up the ramp, you're only changing its potential energy. So all the work that we're doing is resulting in a change in height and thus potential energy for the object. So we need to expand this formula out. The way to calculate work is to multiply force by distance. Okay? To calculate the change in potential energy, I would take m times g times h final and subtract m times g times h initial. In other words, I'm going final potential minus initial potential. Right? Since I start at the bottom, which would be ground level, how much potential energy do I have at the beginning? None. Because my h initial would be 0. And anything times 0 is 0. Right? So I actually don't have to worry about that part. I just have that F times D equals M times G times H final. Since the question wants me to find H final, I just have to move the M and the G over to the other side. How do I do that? Divide, because right now I'm multiplying them all together. Right? So I would divide both sides by M times G. That'll cancel it from that side and bring it over here under FD. All right, now all I have to do is plug in my numbers. So now I've manipulated, now I'm going to solve, or plug in and solve. So our force was 150 times 25 meters divided by, what was the mass? I didn't write it down. Mass was 35 kilograms times G, which is 9.81. All right, when I do that, I should get 10.92 meters. Okay. Does that one follow the same pattern as the ones we did the other day? It does. It's always the same pattern. So once you learn that pattern, all that can change is whether you do the pattern for potential or do the pattern for kinetic. Okay? All right. Try that one. Okay, got a pitcher that throws a ball. The mass of the ball is 0.250 kilograms. They exert 300 newtons worth of force on the ball over a distance of 2.2 meters. Okay? At what speed will he release the ball? What do we have to assume the initial speed is for this question?
0.
Right. We have to assume it's 0. They don't tell us that outright, but the last time I watched baseball, which granted was a long time ago, okay, the guy was holding the ball while he was waiting for the catcher to give him the signal. Okay, so the ball wasn't moving before he started his windup. Okay, the windup is where the work is done. Okay, before the windup, it doesn't have any energy. Okay, give it a try. So again, following the pattern here, I want to write down my givens. I know the mass, I know the force. Okay, so mass equals 0.25 kilograms. Okay, the force being exerted is 300 newtons. The distance over which it is exerted is 2.2 meters. And I know that VI is 0 meters per second. Okay, so you get 1 mark for that if this was a quiz or a test. And this is very much a test level question. Okay. All right, what kind of energy? Is work being done first off? Okay. We know for 2 reasons that work is being done. They told us there was a force and a distance, so definitely work's being done. If I multiply those numbers, it won't be 0. Okay? And secondly, the context of the question. If somebody winds up and throws something, okay, they are changing the energy of the thing they throw. They're making it go faster. All right, so then, work is changing what kind of energy? Kinetic. Right. So you'd get a mark for that. Okay? And maybe you write it like this instead. Maybe you go work equals EK final minus EK initial. Either way is fine. What's my initial kinetic energy? 0, right? If the person is just holding the ball isn't moving, it has no kinetic energy at the beginning of this. Before they start their windup, the ball has no kinetic energy, which means I can take this out because subtracting 0 does nothing. All right, now I can expand out my formula. So force times distance equals m, whoops, not m, equals 1/2 mvf squared. Okay, and vf squared is what I'm looking for, as they want to know how fast they will release the ball. Okay, so if I've got all of that information and I know I'm looking for VF, I need to move some things around. Okay, so I want to leave VF where it is because it's on the top and I want to solve for things when they're on top. What do I do with the half and the m? Divide them over to the other side. Okay, that leaves me with VF squared. I only want VF, so what do? Square root. Okay, so now I can plug in my numbers. So you get a mark for that manipulation, and you probably on a test get a mark for plugging in the numbers. So 300 times 2.2, so 300 newtons was our force, 2.2 meters was our distance. Okay, 1/2 times our mass, which was 0.25. Okay, that will give us our final speed. Okay, my suggestion would be don't try to do this all in one step. All right, so 300 times 2.2, 606 or 6,600. Okay, oh, times 22, 300, 660. Okay, then I'm going to divide that by half times. Okay, now I'm going to divide that by half of 0.25. So 0.5 times 0.25. All right, and then what do I need to do to that number? Square root it. Okay. 72.7 meters per second. Okay, everybody all right with what I did there? basically just like what we did on the quiz and the last kinetic energy problem we did. You getting the theme here? Pattern's always the same. Once we learn the pattern, we can't really mess one of these up. Now, the one thing we haven't done yet is have a question where this energy wasn't zero. And we are going to come across some of those. It doesn't make them any harder. We just have to have a number there. If we want to move it, we would add it to the other side because we'd be subtracting it. So we could just add it over to the other side and we would be okay. All right? It just puts one more number into the equation. Okay, we did one like this. This was my rant day. Okay, about why you have to go the speed limit in a playground zone. Right? So, a car applies its brakes. The brakes apply a force of 10,000 newtons, and it slows from 20 meters per second to 6 meters per second. So, I was foreshadowing when I said we're going to have one where the other one's not zero. Now we have one. Okay. The car's mass is 1,700 kilograms. How far does it travel? Okay. So give it a read, write your givens, decide on the type of energy that's changing, and set it up. I'll give you a little bit of time to get ahead of me, okay? And then we'll have a look at it.